All right, notes, thermal energy, 5.3, using thermal energy. All right, different types of heating systems. This is an old heating system. When people first came to the country in the United States or in the colonies, we used fireplaces. But as our knowledge of heat increased, um, so did the way we heat. All right, we started heating differently. Here's a Franklin stove. Okay. Now the heat radiates out from this, but it's only going to radiate in a not very, it's going to heat one part of the room. Okay. But Ben Franklin created the Franklin stove. We can now move the fireplace, and you can see where the pipe would hook to this. We can now move the fireplace, the Franklin stove, into the middle of the room and heat the entire room through radiation. All right. The heat would send out electromagnetic waves in all directions and heat the house or the building wherever you're at. Nowadays, we use these forced air systems. And what happens is in the furnace, some kind of fuel is burned and the gases escape this way, but the heat is blown into these ducts. All right. And they go around your house and they um, turn or shoot out, blow out hot air. That hot air circulates in the house. As it cools off, it comes back down to the floor and it'll go into the return register and be cycled throughout your house in a convection type of fashion. And here's some vents on your floor. You probably have them on your floor. Let's check it out.
Forced air heating. Your home is equipped with a self-igniting forced air heating system. With the exception of the filter, it is virtually maintenance-free. Should the system need to be reset, instructions can be found on the inside of the furnace panel. The following tips will gain the most efficiency from your system. Ensure the floor and wall registers are fully open and free of any obstructions. Replace the furnace filter every 3 months and sooner if pets are in the home. Date the filter as a reminder when a replacement is due. Heating an unoccupied home wastes money. Programming the thermostat with a minimum 6 degrees offset can realize savings both day and night.
Anywhere. Forced air system. Okay. Radiator systems. This is like what we have a little bit in the school, not quite the same, because these radiators do not sit on the floor. These radiators are up in the ceiling. Like in my classroom, there's a radiator up in the ceiling and there's a vent on that radiator. All right. So what happens is we heat water. Steam gets into these pipes. Steam and hot water. Remember, hot water rises. Um, hot water, hot air rises. So the steam and water get in the system. They go into these radiators, and the radiators heat the room through electromagnetic waves. Not the most efficient in a house, but in a larger area, it's easier to heat a large area like the school with this type of heat. All right. Otherwise, we'd have to have basically a fireplace or something in every room to keep them warm. It's the easiest way to transfer heat through the school. Oh, here's a cat loving some radiator. I saw there was a cat in the book, so I just figured I'd use cats. Electric heating systems. An electric heating system, what happens is we have a blower on here, just like we do in a forced air system. We have heating coils. These coils heat up, they get red hot, bright orange. And the blower blows air across these hot coils. And then the hot air, as a result, as a result, enters the room, right, and is blown into the room. Some electric heaters are radiator heaters, okay, like this one right here. Watch the cat this is amazing. Cat just sits and soaks up the radiation from the electric heater. Looking at his buddy over there saying, hey, man, what's up? Look at the snow outside. Actually, it looks like wallpaper somebody put up, or a shield somebody put up. Anyway. All right, so solar heating. Solar heating, we get our heat from the sun. And you can see here's a little satellite cruising around the sun, one of our satellites. All right, this is a passive system. In a passive system, there is no solar collectors. Heat, the sun is just going to shine down and heat up the room. All right, it'll heat up the room. In an active solar heating system, we have solar collectors. These solar collectors gather the heat, they bring it up down in here and heat up the water or the liquid. Then this water is pumped throughout the house. The heat is put throughout the house with the hot water in this case. Thermodynamics. All right, so thermodynamics. Thermodynamics is a study of heat and work and thermal energy. For work to be done or for heat to exist, and this is what I was telling you earlier, if you rub your hands together, if you're just holding your hands in place, you can, the normal body temperature, put your hands together, do a little bit of work, all right? And when you do that work, your hands heat up. Now, your hands cannot heat up more than the work you do, all right? The more work you do, the warmer they're going to get. Faster you rub them together, the more work is done, and the more heat you're going to generate. I believe this was a video, but it's not working. So, all right. Heat and work increase thermal energy. So this person's cold. They got a nice fire going. They put their hands down by the fire to warm them. They'll rub them together also sometimes, like this person's doing. All right. It increases the heat. You're doing work to raise that thermal energy, but it will help warm up your hands even faster if you do work. All right, the first law of thermodynamics. Basically, it's telling us here's the energy before and the energy after. It's even, okay, even Steven. If I want to get 100 joules of heat energy into my hands to warm my hands up, I have to burn 100 joules of energy or of fuel stored in my body. Energy cannot be created or destroyed. Energy always stays the same. All right, it always stays the same. So I have to burn energy. I have to burn some of the fat in my body, and I got some, trust me. I need to burn some of that energy to get the heat. Okay, it just doesn't happen automatically. Conservation of energy. It's a transformation from the chemical potential energy of my body into the energy of work, the rubbing of my hands together. I'm sitting here rubbing my hands together. I know you can't see me, but that energy from the chemical potential energy in my body, rubbing my hands together gives me heat energy. It is a transfer of energy. That is the first law of thermodynamics.
Hello there. It's the easy engineering once again, and today's topic is the first law of thermodynamics. The first law of thermodynamics says that heat is a form of energy, and as what all other forms of energy is subject to, it follows the law of conservation of energy. So what does this mean? It means that heat energy also cannot be created nor destroyed and can only be transferred to one form or another. Don't overthink this too much. This law is all about heat as energy and follows the law of conservation of energy. And that's it. Now to appreciate the application of this law, let's try a very good one example. This coal is just a type of rock, right? But for scientists, this rock contains an energy that produces heat energy when it undergoes a complete combustion. Actually, some power plant utilizes this coal to generate electrical energy, or what we call as electricity. What they do is that they feed this coal into a boiler furnace, and with an assistance of oxygen and a little heat, this creates a combustion in a form of heat energy. Now, the heat energy will transfer its energy to water above it, making it into a steam. And the steam will rotate a turbine, and that's a mechanical energy right there. And then this turbine will rotate a generator which converts that energy into electrical energy. See that just by knowing this law, you can do so much. And that's it. This is easy engineering. See you again for our other easy and fun engineering topics.
All right. So, as you can see there, um, the knowledge of convection, conduction, radiation, the knowledge of um, how that thermal energy is transferred lets us um, create, as you just saw in that video, create electricity. Okay. We've gone from chemical potential energy into heat energy, into the energy of that water, convection current, which causes the turbine to spin, and we can transfer this energy stored in the coal into electrical energy. Isolated and non-isolated systems.
In this tutorial, I'm going to briefly discuss the difference between an open system, a closed system, and an isolated system. So let's start with an open system. So I'm going to draw an open container with water. So the stuff inside is the system, in this case the water. Now, in an open system, you need to realize that mass, or basically matter, can flow into and out of an open system. So like oxygen gas, it can enter and it can leave the system. Now the second thing is energy. Energy such as heat or even light can flow out of or into the system as well. And so that's an open system. Both energy and matter can flow into or out of such a system. In a closed system, in this case I'm going to draw a sealed container. Matter cannot flow into or out of a closed system. So oxygen gas from the air cannot enter. So I'm just going to put an X. However, heat energy can flow out of or into the system. So a closed system is not insulated to heat. Heat can easily flow into or out of the system. Now, in an isolated system, we have a closed container that is very well insulated. So like a closed system, matter cannot enter and matter cannot leave. So water cannot escape out of this closed system. And this time, heat energy cannot escape either. And heat energy cannot enter. So it's extremely well insulated. So in an isolated system, nothing can enter and nothing can leave. So just to review, in an open system, matter and energy can enter or exit an open system. In a closed system, matter cannot transfer into or out of a closed system, but energy can. And in an isolated system, nothing can enter, nothing can leave. Matter and energy cannot enter or leave an isolated system. And so those are the differences between these three systems.
Okay. Now, the second law of thermodynamics, heat flows always from hot to cold, always from hot to cold.
Hello there, it's the Easy Engineering once again, and today's topic is the second law of thermodynamics. This topic has made most of the engineering students confused, so for this discussion, we will make it as easier as possible. So the major statements of the second law of thermodynamics are the following. First is a closure statement that says it is impossible for any statement to operate in such a way that the sole result would be an energy transfer by heat from a cooler to a hotter body. Second is Kelvin-Planck statement. It is impossible for any system to operate in a thermodynamic cycle and deliver a net amount of energy by work to its surroundings while receiving energy by heat transfer from a single reservoir. Third statement is the entropy statement. It is impossible for any system to operate in a way that entropy is destroyed. So, to make it easy, we made two easier statements that would help us more in understanding this law. So first is, well, let's call this as high to low. For any process, a natural flow will always be from higher energy value to lower energy value. For example, coffee. The temperature of coffee is higher than its cup, and as what it says, from higher energy value. So the temperature of coffee gets transferred to the cup, which is cooler, lower energy value, and that's why the cup gets hotter. Or try a compressed gas in a balloon. If you open a small hole in a balloon, does the outside air enters the balloon? No. Instead, the gas in the balloon goes outside, transfers its pressure to the outside air, because the gas in balloon has higher pressure than the outside air. A tank full of water connected to an empty tank with a valve in the middle. Now open the valve, and what happens? The full tank level is lowered, transferring its level to the empty tank. How about the topics being discussed in your classroom? The transfer of ideas comes from the professor, which has more ideas, to its students, which has lower ideas. Or even think of the salary from employer to employee. True, right? So now, let's move to the second one. Let's call this as perfect is impossible. For every real world process, there will always be losses. That means you cannot convert all of your car's fuel into mechanical energy which can rotate your car's wheels. Proof is the gases you see on the car's muffler. Or try bouncing a ball by first throwing it up to the air. See that as the number of bounces increases, the level of bounce decreases because of the loss of energy which is transferred to the ground. How about our foods? That is our source of energy. We can see the losses through our sweat, urine, and solid waste. So that's it. I hope we made it easier for you. Before this video ends, we would like to make a note that second law of thermodynamics is a law, and it is applicable to everything in our world. I hope this changes your perspective on this law, and if you have comments or you want to correct us, please comment below. We would love to listen. Thank you for watching, and see you again for our other easy and fun engineering topics. Easy Engineering topics made easy and fun for you.
Okay, so the big thing is um, hot to cold. Heat moves from hot to cold. Okay, here is converting thermal energy into mechanical energy. They've put a liquid in here. As it boils, it's going to shoot steam out, making this wheel move.
ಇಲ್ಲಿ ಇಂಧನ ಶಕ್ತಿಯು ಶಾಖಶಕ್ತಿಯಾಗಿ, ಶಾಖಶಕ್ತಿಯು ಹಬೆ ಶಕ್ತಿಯಾಗಿ, ಹಬೆ ಶಕ್ತಿಯು ಯಾಂತ್ರಿಕ ಶಕ್ತಿಯಾಗಿ ಪರಿವರ್ತನೆ ಆಗ್ತಾ ಇದೆ. ಧನ್ಯವಾದಗಳು.
Now, a heat engine. All right, an internal combustion engine. This is what goes on in your car. And these are all ways we're transferring thermal energy to mechanical energy.
Science, please! Do the words auto mechanics make you curious? Actually, it's a cinch. A car is made up of wheels, seats, fuzzy dice, a body, and an engine. The internal combustion engine. The engine works in 4 stages. First, a valve opens and the piston lowers, letting a mixture of fuel and air into the combustion chamber. Second, as it comes up, the piston compresses the fuel-air mixture. Third, a spark from the spark plug ignites the mixture, which pushes the piston down again. Fourth, the exhaust valve opens and as it comes up, the piston pushes the spent gases out. And the cycle starts over again. Intake, compression, combustion, exhaust. Intake, compression, combustion, exhaust. Intake, compression, combustion, exhaust. Intake, compression, combustion, exhaust. The movement of the engine is transmitted to the wheels for the driver's delight.
All right. Efficiency of heat engines. Okay, so the efficiency of a heat engine. They're not greatly efficient. A lot of energy is wasted in. Remember, you can't create or destroy energy, but even in a car, energy is wasted. They're not very energy efficient. They're not very. You've heard the word fuel efficient. Most of the energy is transferred into heat. If you were to touch a car engine, you'd burn your hand. The exhaust is hot. All of this is, we could say, wasted energy. All right. So efficiency of a heat engine is not the best. All right. Doing work to transfer thermal energy. This is the reverse process where cold goes to hot. You put in a warm object and it becomes cold. It reverses the process, but these are known as heat engines, heat movers. Okay. So this refrigerator, and if you know, on the back of a refrigerator, it has a coil, and that coil gets burning hot. All right. As it takes the heat out of these products and puts cold in. Also, an air conditioner is a heat mover. It takes the heat out of the room and replaces it with cool air. And heat pumps do the same type of thing. They draw out heat and they put in cool air. That is it. Energy transformations and thermal energy. I hope this helps with your notes or with your homework and studying for the test.